Welcome back, everyone, to the deep dive. So, if you've been following AI at all lately, you've probably seen this term mixture of experts popping up more and more. It's got to be a pretty big deal when it comes to LLMs, those really big, powerful language models. And that's what we're going to be diving into today, what it is and why it matters, why people are even talking about it.
Yeah, definitely. It's a pretty ingenious way to get around some of the roadblocks that have been kind of slowing down AI development.
hmm
Especially when we talk about how much these models cost to run and just how big they can get, before they just become too unwieldy to actually use.
Right. I mean, we all see the headlines about these models with trillions of parameters, but, at a practical level, what does that even mean?
It's actually pretty simple when you break it down. So instead of having one massive neural network that's trying to do everything.
Which is how we've always kind of thought about these models, right?
Yeah, right. Exactly. So instead of that one giant model, imagine you have a whole team of specialists. Each one is really good at a particular task or understands a certain type of data really well. These are the experts.
Okay, I'm starting to get the picture. So instead of one super generalist, we've got a bunch of hyper-focused experts.
Exactly. And then you have this other component called the gating network. Think of it like a traffic controller. It looks at the incoming information.
Like a question we ask the model.
Yeah, exactly. It looks at that input and decides which expert or experts are the best ones to handle it.
So some experts might be really good at understanding grammar, while others might be better at, figuring out the context of a question. For example.
Exactly. And that's where the real power comes in. Because instead of activating the entire model for every single input.
Which would be incredibly inefficient, right?
Oh, yeah. With a mixture of experts, you only activate the parts of the model that are actually relevant to the task at hand.
Okay, so this gating network, it's learning how to sort of direct traffic to the right experts. How does it figure out who's best suited for a particular task?
So during training, because remember, these models have to be trained on huge amounts of data, the gating network is also learning alongside all the experts. It's basically learning to predict which expert or combination of experts is going to give the best results for a particular type of input.
So it's like it's developing its own intuition about which expert is most likely to have the answer.
In a way, yeah. And it's not just a one-to-one mapping either. The gating network actually assigns probabilities to the experts. So it might say, okay, for this input, there's an 80% chance that expert A is the best fit, but there's also a 20% chance that expert B might have something useful to contribute.
So it's hedging its bets, kind of.
Exactly. It's not just a rigid deterministic system. There's a certain level of probabilistic decision-making happening there.
That's really interesting. So we've got these individual experts that are being trained on specific types of data, and we've got this gating network that's learning how to direct traffic to the right expert. What's the big picture here? Why is this so significant?
Well, first of all, you touched on it earlier, efficiency. By only activating the parts of the model that are actually needed, you're saving a ton of computational power. This means faster response times, which is crucial for, any kind of real-world application where you don't want people waiting around for the AI to think.
Right. Nobody wants to sit there staring at a spinning wheel while their AI assistant tries to figure out what they're asking.
Exactly. But it goes beyond just efficiency. It also allows these models to scale to, ridiculously huge sizes.
We're talking about the models with trillions of parameters.
Yeah. Without a mixture of experts, those kinds of models would be practically impossible to train and run. They'd just be too computationally expensive.
So this is how we're getting to these next level language models that can do all sorts of crazy things.
It's a big part of it, yeah. And with that increased scale, you also get better specialization because each expert can really focus on its particular domain and become incredibly proficient. It's like if you had a question about, I don't know, astrophysics, you'd rather ask an astrophysicist than a general practitioner, right?
So it's not just about the brute force of having trillions of parameters. It's about having the right expertise in the right place.
Exactly. And that specialization leads to better accuracy, better performance on all sorts of different tasks.
Okay, so efficiency, scalability, specialization, all huge advantages. Are there any other benefits to using mixture of experts?
Yeah, actually. There's also the flexibility of the architecture. You can add new experts or modify existing ones without having to retrain the whole model from scratch.
So it's more modular, you can swap out parts as needed.
Exactly. And that makes it much easier to adapt to new data, add new capabilities, keep the model up to date as things change.
That makes a lot of sense. I guess the traditional approach would be like, okay, we need to update the model. Let's go back to square one and retrain the whole thing.
Yeah, which would be a huge undertaking. And then there's the fault tolerance. If one expert has a problem, it doesn't necessarily bring down the whole system.
Because the other experts can still function independently.
Right. It's kind of like having a backup generator. If one part of the system fails, the rest can still keep running.
Okay, so all very compelling reasons to use mixture of experts, but I'm guessing there are also some challenges involved.
Oh, yeah, definitely. It's not all sunshine and roses. One of the biggest hurdles is the complexity of training these models. Coordinating the gating network with, potentially hundreds or even thousands of experts is a really tricky optimization problem.
I can imagine. Trying to make sure all those moving parts are working together in harmony.
It's a delicate balancing act, for sure. And then there's the inference overhead. Even though you're only activating a subset of experts, you still have to route the input through the gating network.
So there's still some added complexity there, even though it's more efficient overall.
Yeah. And if the gating network decides to activate multiple experts, which it often does.
Because sometimes you need multiple perspectives to solve a problem.
Exactly. Well, that can still put a strain on resources, especially if you're trying to run these models on devices with limited memory and processing power.
Like smartphones or other edge devices.
Yeah. And then there's the issue of load balancing. You want to make sure all your experts are being utilized effectively. You don't want some experts sitting idle while others are getting overloaded with work.
Right. Because that would defeat the purpose of having all these specialized experts in the first place.
Exactly. So there's still a lot of ongoing research and development focused on, improving these aspects of mixture of experts. But even with those challenges, we're already seeing MOE having a major impact in a lot of different areas.
So let's talk about some real-world applications.
Yeah.
We touched on multilingual models earlier. How is mixture of experts being used there?
Well, one example is Microsoft's Z-code model. It basically has experts that specialize in different languages or families of languages. So the gating network can direct text to the appropriate expert or combination of experts to get the most accurate translation.
So it's like having a whole team of translators, each one fluent in a specific language or group of languages.
Yeah, that's a good way to think about it. And it's not just translation either. MOE is being used for all sorts of NLP tasks like text summarization, question answering, even things like code generation.
And what about computer vision? I know MOE is making waves there as well.
Yeah, so Google has these things called vision transformers, or VMOs. Instead of processing an entire image all at once, they break the image down into smaller patches and send those patches to specialized experts.
So some experts might be really good at recognizing edges or textures, while others might be better at identifying objects.
Exactly, and that allows the model to process images much more efficiently and accurately.
So it's the same basic principle of mixture of experts, but applied to a completely different type of data.
Yeah. And it's not just Google either. A lot of companies are starting to incorporate MOE into their computer vision models.
Okay, so we're seeing MOE being used in a lot of different applications across different domains, which leads me to the question, which specific LLMs are currently using mixture of experts?
So one that's gotten a lot of attention is OpenAI's GPT-4. They haven't officially confirmed the architecture, but there's a lot of evidence to suggest that it's using MOE.
Which would make sense given how powerful it is and how quickly it can generate text.
Right. And then there's Mistral AI's Mixtral 8x7b model. That one explicitly uses MOE. It has 8 experts, each with 7 billion parameters, and for each input, it activates 2 of those experts.
So even though each expert is relatively small, the combined model is incredibly powerful.
Exactly. And they've actually shown that this approach leads to faster inference and lower computational costs compared to a dense model of the same size.
So it's not just about building bigger models, it's about building smarter models.
Right. And we're also seeing MOE being used in these more multimodal AI systems that can handle different types of data, like text, images, audio, even video.
Like Google's Gemini 1.5 and IBM's Granite 3.0.
Exactly. Those are both good examples of how MOE is being integrated into these more complex multimodal architectures.
So it really seems like mixture of experts is going to be a key technology going forward in AI development. Where do you see things heading in the future?
Well, there's a lot of research being done on improving the routing algorithms, making the gating network even better at deciding which experts to activate.
So fine-tuning the traffic controller, so
Yeah.
to speak.
Yeah, and then there's the whole area of multimodal MOE, which I think is going to be huge. Imagine a model that has experts for language, images, audio, all working together seamlessly.
That would be pretty incredible.
And then on a more practical level, I think we're going to see MOE becoming more and more accessible to a wider range of developers. There are already some open source projects out there that are making MOE technology more widely available.
So we might start seeing MOE popping up in all sorts of unexpected places.
I think that's a very real possibility.
Okay, so to wrap things up, what's the key takeaway about mixture of experts?
I think the main thing to understand is that it's a fundamental shift in how we're thinking about building these large language models. It's not just about brute force anymore. It's about specialization, efficiency, adaptability.
And ultimately, it's about building AI systems that are more powerful, more versatile, and more aligned with how humans actually think.
Absolutely.
And on that note, here's a thought for our listeners. If AI is starting to leverage specialized knowledge in this way, maybe we can learn something from that. Maybe instead of trying to be a jack of all trades, we should focus on developing our own areas of expertise. Maybe that's the key to thriving in a world where AI is becoming more and more capable.
That's an interesting idea, something to think about for sure.
Thanks for listening, everyone. We'll see you next time on The Deep Dive.